On the evening of January 3, 1961, the Stationary Low-Power Reactor Number 1 operated under normal maintenance conditions. Control systems functioned within design parameters. Instrumentation displayed expected readings. Recording devices captured routine operational data as they had for months of previous operation. At 21:01 hours, the reactor experienced a power excursion that destroyed the core and killed 3 technicians. The event lasted approximately 4 milliseconds. When investigators attempted to reconstruct the excursion sequence, they discovered that the reactor's data recording systems had captured everything except the critical measurements that defined the failure itself. Temperature readings, neutron flux data, and pressure measurements that would have revealed the excursion's physics simply did not exist in the recorded logs. The instrumentation had functioned exactly as designed, monitoring what it was built to monitor, recording what it was programmed to record. This was not a case of equipment failure or human error during the emergency. The recording systems operated precisely according to their design specifications. They measured normal parameters during normal conditions and stopped measuring when conditions became abnormal. The most crucial 4 milliseconds in the reactor's operational history remained invisible because the monitoring architecture had been optimized for steady-state operation rather than transient analysis. The reactor's failure became forensically opaque not despite its instrumentation systems, but because of them. How can a monitoring system function perfectly and still render critical system behavior invisible to analysis? The SL-1 reactor represented the synthesis of multiple design philosophies that, when combined, created a monitoring architecture fundamentally mismatched to the physics it was meant to observe. Designed as a prototype for the Army's distant early warning system installations in remote Arctic locations, the reactor embodied competing requirements that shaped every aspect of its instrumentation and recording systems. The facility needed to operate for 3 years without refueling, maintain itself with minimal technical support, and provide both electrical power and building heat in environments where conventional logistics were impossible. These operational requirements drove the selection of a boiling water reactor design that eliminated the complexity of steam generators and secondary cooling loops. The reactor employed highly enriched uranium fuel at 93% U-235 concentration, similar to naval propulsion reactors, packaged within a compact 3-megawatt thermal system. The core contained 40 aluminum fuel assemblies, arranged in a geometry that prioritized thermal output over operational monitoring comprehensiveness. The reactor's control system reflected this design philosophy through its use of only 5 cruciform control rods rather than the larger arrays typical of power reactors. 4 outer shim rods, designated as numbers 1, 3, 5, and 7, provided general reactivity control, while a single central control rod, number 9, regulated reactor power. This simplified control scheme reduced maintenance complexity, but concentrated enormous reactivity worth in individual components, particularly the central rod. The instrumentation architecture that monitored this system was designed around assumptions about how nuclear reactors behave during normal operation. Recording systems captured temperature, pressure, neutron flux, and control rod position data at sampling intervals optimized for the thermal time constants of steady-state operation. The data acquisition equipment employed analog recording devices with response times measured in seconds, appropriate for monitoring gradual power changes and thermal transients that developed over minutes or hours. This temporal resolution reflected a fundamental design assumption that all operationally significant reactor behavior would evolve slowly enough for recording systems to capture meaningful data. The monitoring philosophy presumed that nuclear excursions, if they occurred at all, would develop gradually and provide operators with recorded data streams that could guide corrective actions. The instrumentation was designed to observe and record the reactor's approach to potentially dangerous conditions, not to capture the conditions themselves. The neutron flux monitoring system exemplified this design philosophy. Neutron detectors positioned around the core generated electrical signals proportional to neutron density, which were processed through analog circuits that conditioned the signals for recording equipment. The signal processing chains included filtering circuits that removed high-frequency noise but also imposed response time limitations measured in hundreds of milliseconds to several seconds. These processing delays ensured stable, clean signals for recording but created systematic blind spots for rapid transients. Similarly, the control rod position indication system was designed to track gradual rod movements during normal power operations. Position sensors mechanically coupled to the control rod drive mechanisms provided electrical signals that indicated rod height relative to the core. The signal processing and recording systems for rod position data were optimized for the slow, controlled movements typical of power maneuvering operations with response times adequate for tracking movements over minutes or hours, but inadequate for rapid manual manipulation. The reactor's data recording infrastructure reflected 1950s technology limitations that further constrained the system's ability to capture rapid events. Chart recorders with paper-based data storage provided continuous logging of key parameters but operated at fixed time scales that prioritized long-term trending over transient capture. The recording devices could not be reconfigured for high-speed data acquisition during abnormal events, because their design assumed that abnormal events would develop within their standard operational envelope. This recording limitation was not recognized as a significant constraint, because the reactor's safety analysis did not contemplate scenarios that would exceed the instrumentation system's temporal resolution. Safety calculations focused on thermal hydraulic transients, loss of coolant accidents, and control system malfunctions that would develop over time periods compatible with the monitoring architecture. The possibility of prompt criticality excursions developing in milliseconds was not considered credible within the reactor's operational envelope. The core geometry and fuel loading further reinforced these monitoring assumptions. The reactor employed burnable poison strips made of aluminum-boron alloy that were spot-welded to fuel assemblies to extend core life and reduce control rod requirements. These strips created a complex, non-symmetrical neutron flux distribution that made accurate reactor physics calculations difficult, but was assumed to provide inherent stability that would prevent rapid reactivity changes. By the time of the accident, the SL-1 had accumulated 932 megawatt days of operation, and the burnable poison strips were showing significant degradation. The strips were buckling, flaking, and creating debris that interfered with control rod movement. But the monitoring systems were not designed to detect or quantify these material condition changes. The instrumentation could observe the symptoms of degradation through increased control rod sticking frequency, but it could not measure the underlying physical changes that were reducing shutdown margins and increasing the reactor's vulnerability to rapid reactivity insertion. The recording systems faithfully documented the increasing frequency of control rod operational problems, showing that rods exhibited sticking behavior approximately 2% of the time through November 1960, increasing to 13% between November 18 and December 23, 1960. This data provided clear evidence of worsening material conditions, but the instrumentation philosophy interpreted these problems as mechanical maintenance issues rather than indications of fundamental changes in reactor physics behavior. The reactor's shutdown margin monitoring exemplified the limitations of the recording-based operational philosophy. Reactivity calculations required detailed knowledge of fuel burnup, poison strip condition, water temperature, and xenon decay effects, but the monitoring systems were not designed to provide real-time measurements of these parameters. Instead, shutdown margin assessments relied on periodic calculations based on recorded operational history, creating significant uncertainty in the actual reactivity state of the core. This uncertainty was compounded by the reactor's complex geometry and the difficulty of accurately modeling the irregular burnable poison distribution. Pre-accident calculations for predicting criticality conditions were acknowledged to be grossly oversimplified and deviated significantly from observed reactor behavior. The monitoring systems could record the symptoms of these calculational inadequacies through discrepancies between predicted and actual control rod positions, but they could not provide the real-time reactivity measurements needed to understand the reactor's true physics condition. The installation of additional cadmium shim strips in November 1960 to address degraded shutdown margin illustrated both the limitations of the monitoring philosophy and its false confidence in recorded data. The decision to install only 2 shim strips in positions 2 and 6 rather than 4 strips in a symmetrical arrangement was based on calculational models rather than direct measurements, and the monitoring systems could not detect that one of the installed strips was mispositioned by 2.5 inches below its intended location. This mispositioning created local power peaking that would be discovered only during post-accident examination of the damaged core, demonstrating that the reactor's actual physics configuration was significantly different from what the monitoring systems indicated. The recording devices faithfully captured the reactor's response to these hidden configuration errors through increased power oscillations and control instabilities, but the data was interpreted within the framework of the assumed core geometry rather than as evidence of actual geometry problems. The reactor's operating history in its final months revealed the progressive failure of the monitoring philosophy to provide adequate system understanding. High-power testing at 4.7 megawatts to evaluate a new condenser pushed the reactor beyond its stable operating envelope, creating power oscillations that caused control system instability and automatic scrams. These events were recorded as boiling noise that swung recorder pens off their charts, but the instrumentation was not designed to capture the detailed physics of these oscillations or their implications for reactor stability. The maintenance procedure that ultimately led to the accident was developed within this monitoring framework that assumed all significant reactor behavior would be observable through recorded data. The procedure for reconnecting control rod drives required manually lifting each 84-pound control rod assembly approximately 3 inches to allow drive mechanism coupling, a task that was considered routine based on the assumption that control rod position would be accurately monitored and recorded throughout the process. This assumption proved fatal because the rod position indication system was not designed to accurately track rapid manual movements, and the recording systems could not capture the dynamics of prompt criticality conditions that developed when the central control rod was withdrawn beyond its design envelope. The monitoring architecture that had been optimized for steady-state operations became a systematic blind spot for the transient conditions that defined the accident. The reactor's instrumentation and recording systems functioned exactly as designed on the evening of January 3, 1961. They monitored routine parameters, recorded steady-state data, and provided no indication of the developing catastrophe because they were never intended to observe catastrophic conditions. The 4 milliseconds that destroyed the reactor occurred in a temporal domain that simply did not exist within the monitoring system's design universe. This fundamental mismatch between reactor physics time constants and monitoring system capabilities was not recognized as a design vulnerability because the safety analysis framework did not contemplate scenarios that would expose these limitations. The reactor was assumed to be inherently safe against rapid reactivity insertion because the monitoring systems provided no evidence that such insertion was possible within the operational envelope they could observe. The training protocols that governed SL-1 operations were built upon the same temporal assumptions that shaped the reactor's instrumentation architecture. Personnel preparation emphasized the interpretation of recorded data streams rather than direct physical observation of reactor behavior, creating a cognitive framework that aligned operator mental models with the limitations of the monitoring systems they were trained to trust. The reactor's operating organization reflected the Army's approach to nuclear technology deployment, which prioritized operational simplicity over technical depth. The facility was operated under contract by Combustion Engineering, but the actual reactor operations were performed by young military technicians with limited nuclear engineering backgrounds. None of the 3 crew members on duty during the accident had formal training in nuclear engineering or reactor physics. Instead, receiving specialized instruction focused on procedural compliance and parameter monitoring. This training approach was intentionally designed to enable reactor operation by personnel without extensive technical education, consistent with the Army's requirement that these reactor plants be maintainable in remote locations by enlisted technicians. The instructional curriculum emphasized recognition of normal parameter ranges, response to alarm conditions, and execution of predetermined procedures, rather than fundamental understanding of reactor physics or system dynamics. The training program's reliance on recorded data interpretation created a systematic dependence on the same monitoring systems that would prove inadequate during the accident. Trainees learned to assess reactor condition through chart recorder traces, logged parameter values, and instrumented readings, rather than through direct observation of physical phenomena. This educational framework implicitly assumed that all operationally relevant reactor behavior would be visible through the data recording systems. Simulator training was limited by the same temporal constraints that affected the actual reactor monitoring systems. Training scenarios focused on gradual transients that developed over time periods compatible with recording system capabilities, reinforcing the assumption that reactor emergencies would provide adequate time for data-based decision-making. The possibility of events that exceeded the monitoring system's temporal resolution was not included in the training curriculum because such events were not considered credible within the reactor's designed operational envelope. The maintenance procedures that defined control rod drive reconnection work were developed within this training framework that emphasized recorded verification of system status. The procedure required operators to manually lift control rods during drive mechanism coupling, but provided no guidance for recognizing or responding to conditions that might develop faster than the position indication systems could track. The procedural assumption was that control rod movement would always be observable through normal instrumentation channels. This procedural framework had evolved through 2 years of reactor operations that consistently reinforced confidence in the monitoring system's adequacy. Routine maintenance activities had always been successfully completed with full instrumentation coverage, creating operational experience that validated the assumption that significant reactor behavior would always be visible through recorded data. The absence of previous incidents involving rapid transients was interpreted as evidence that such transients were not possible, rather than as evidence that the monitoring systems were not designed to detect them. The reactor staffing model further embedded these limitations into the operational culture. Combustion Engineering's request for funding to provide supervisory coverage during all 3 shifts had been denied by the Atomic Energy Commission, leaving the evening and night shifts to operate without senior oversight. This staffing limitation meant that the least experienced personnel were responsible for complex maintenance activities, without immediate access to engineering support that might have recognized the monitoring system's limitations. The crew scheduling that placed 3 relatively inexperienced technicians alone at the facility on January 3 reflected this organizational framework that prioritized cost containment over technical depth. The evening shift crew was expected to execute maintenance procedures based on their training and recorded parameter monitoring, without engineering supervision, that might have provided alternative assessment capabilities during abnormal conditions. The procedural verification processes that governed maintenance activities were entirely dependent on recorded data streams for validation of work completion. Quality assurance protocols required documentation of system parameters before, during, and after maintenance activities, but these protocols assumed that the monitoring systems would provide continuous coverage of all significant system changes. The verification framework had no provisions for conditions that might develop outside the recording system's operational envelope. The reactor's alarm system design reflected the same monitoring philosophy that shaped training and procedures. Audible and visual alarms were triggered by preset parameter thresholds that were established based on steady-state operating experience and gradual transient analysis. The alarm logic assumed that dangerous conditions would develop slowly enough for the monitoring systems to detect parameter changes and provide advance warning to operators. These alarm set points were calibrated for thermal hydraulic transients and gradual power changes rather than prompt criticality conditions that could develop in milliseconds. The alarm system was designed to alert operators to trends toward potentially dangerous conditions, not to announce the arrival of conditions that had already exceeded safe limits. This temporal mismatch meant that the most dangerous reactor conditions would generate no alarms because they would develop and resolve faster than the alarm system could respond. The control room interface design reinforced operator dependence on recorded data through the physical layout of monitoring equipment and information displays. Chart recorders, meter displays, and alarm panels were arranged to facilitate steady-state monitoring and trending analysis rather than rapid event recognition. The human factors engineering assumed that operators would have adequate time to consult multiple data sources and correlate information across different measurement systems before making operational decisions. The maintenance procedure execution environment created additional human factors constraints that degraded the crew's ability to recognize developing problems. The work was performed on the reactor vessel head, with personnel positioned directly above the core during control rod manipulation, a configuration that provided excellent access for mechanical work but eliminated direct visual observation of control room instrumentation. The crew members performing the control rod work were physically separated from the monitoring systems that might have detected abnormal conditions. The communication protocols between crew members during maintenance activities relied on verbal confirmation of procedural steps rather than independent verification of reactor parameters. The assumption was that individual crew members could reliably assess system condition through their assigned responsibilities, without continuous cross-checking of monitored parameters. This communication framework provided no redundancy for detecting conditions that exceeded individual crew members' observational capabilities. The reactor's operational history during its final months had created additional latent conditions that degraded the effectiveness of human factors safeguards. The increasing frequency of control rod sticking events had led to informal procedural modifications that emphasized mechanical force application to overcome binding conditions. These modifications were accepted by supervision as necessary adaptations to equipment degradation, but they created normalization of conditions that required operators to exceed standard procedural limits. The crew's previous experience with control rod binding during maintenance activities had established behavioral patterns that prioritized procedural completion over parameter monitoring. When control rods stuck during withdrawal, the standard response was to apply additional manual force until the rods moved freely, a practice that had been successfully employed multiple times without adverse consequences. This operational experience created confidence that manual rod manipulation could be safely accomplished without detailed monitoring of rod position or reactivity effects. The reactor's recent operational problems had also created schedule pressures that influenced crew behavior during maintenance activities. The facility was scheduled to restart on January 4 after an extended outage for maintenance and modifications, creating time pressure to complete all necessary work within the available window. This schedule constraint encouraged efficient procedural execution, rather than detailed verification of each step through recorded parameter monitoring. The training program's emphasis on procedural compliance over technical understanding created a cognitive framework that discouraged questioning of established procedures or recognition of conditions that fell outside normal operational experience. Crew members were trained to execute predetermined sequences of actions based on standard conditions, rather than to adapt their behavior based on real-time assessment of system physics. This training approach was effective for routine operations but provided no foundation for recognizing or responding to conditions that exceeded the monitoring system's design envelope. The reactor's safety culture reflected broader military and industrial approaches to nuclear technology that emphasized procedural discipline over technical innovation. The operational framework discouraged crew-level modifications to establish procedures and reinforced reliance on approved methods that had been validated through previous operational experience. This culture was appropriate for preventing unauthorized changes to safety-related procedures, but also prevented recognition of situations where standard procedures might be inadequate. The evening of January 3 represented the convergence of all these latent conditions into a configuration that maximized the likelihood of monitoring system limitations becoming operationally significant. 3 experienced, but not senior technicians were working alone on a complex maintenance task that required manual manipulation of safety-critical components, without engineering supervision or detailed real-time monitoring of reactor parameters. The crew's training, procedures, and operational experience had all reinforced confidence in the adequacy of standard monitoring and verification processes for control rod maintenance activities. The possibility that their work might create conditions that exceeded these monitoring capabilities was not considered because their entire operational framework assumed that such conditions could not develop within the reactor's normal operational envelope. When the central control rod was lifted during drive mechanism reconnection work, The crew was performing a routine procedure that had been successfully completed multiple times in the past. Their training and experience provided no indication that this particular procedural step might create conditions that would develop faster than they could observe, understand, or control. The maintenance procedure that would destroy the SL-1 reactor began as a routine task that had been successfully completed dozens of times during the facility's operational history. The reconnection of control rod drive mechanisms following flux wire installation required precise mechanical alignment between control rod assemblies and their motor-driven positioning systems, work that demanded careful coordination but had never previously challenged the reactor's monitoring capabilities. The procedure called for manual lifting of each control rod approximately 3 inches above its fully inserted position to allow installation of the mechanical coupling that connected the rod to its drive motor. This lifting operation was performed using a T-shaped handling tool that clamped onto the upper end of each rod assembly, enabling crew members to manually raise the 84-pound control rod and blade assembly to the required height for coupling installation. The central control rod, designated as number 9, was the last rod to be reconnected during the evening shift's work schedule. By 21 hours, the crew had successfully completed drive reconnection for the 4 outer rods and was proceeding with the final step required before reactor startup preparations could begin. The central rod had been partially lifted earlier in the procedure to allow installation of a stop washer and retaining nut, indicating that the mechanical coupling process was proceeding normally. The position indication system that monitored control rod height was designed to track the gradual movements typical of powered rod operation during reactor power changes. The system employed mechanical linkages between rod drive motors and electrical position transmitters that generated signals proportional to rod height above the core. These position signals were processed through analog circuits that provided rod height information to control room displays and chart recorders. The position indication system's response characteristics were optimized for the slow, controlled movements that occurred during normal reactor operations when rod positions changed over periods of minutes or hours. The electrical circuits that processed position signals included filtering components that removed high-frequency noise but imposed response delays measured in hundreds of milliseconds. The system was never intended to accurately track rapid manual movements that might occur during maintenance activities. When maintenance procedures required manual rod manipulation, the position indication system was typically bypassed or ignored because the mechanical coupling process occurred with control rod drives electrically disconnected from their normal operating circuits. The assumption was that manual rod movements would be small, controlled, and easily observable through direct, visual inspection of the rod handling process. The position indication system's inability to track rapid manual movements was not considered operationally significant because manual movements were assumed to be inherently limited in both speed and magnitude. The central control rod's withdrawal began as specified in the maintenance procedure, with one crew member grasping the T-handle tool and applying upward force to lift the rod assembly the required 3 inches above its seated position. The rod initially resisted movement, exhibiting the sticking behavior that had become increasingly common during the reactor's final months of operation. This sticking was attributed to mechanical interference between control rod blades and their guide shrouds, a condition that had been repeatedly observed and successfully overcome through application of additional manual force. The crew member performing the lifting operation responded to the rod's resistance by applying greater upward force, following the informal procedures that had evolved through months of experience with control rod binding problems. Previous successful completion of similar operations had established confidence that additional force could safely overcome mechanical interference without adverse consequences. The operational culture had normalized the use of increased manual effort to compensate for equipment degradation. The moment at which the central control rod broke free from its stuck position marked the beginning of a divergence between physical reality and system perception that would prove irreversible. The rod's sudden movement under applied manual force resulted in rapid withdrawal that exceeded both the intended lifting distance and the position indication system's ability to track the movement. The mechanical coupling between rod position and electrical indication was severed by the speed and magnitude of the withdrawal. The position indication system's response to this rapid movement demonstrated the fundamental mismatch between maintenance procedure requirements and monitoring system capabilities. The electrical circuits that processed rod position signals could not respond fast enough to track the rod's movement, creating a temporal gap during which the rod's actual position diverged from its indicated position. The monitoring system continued to display the rod's previous position, while the physical rod moved to a new position that placed the reactor in a supercritical configuration. This divergence occurred within a time frame that prevented any possibility of recognition or corrective action. The rod withdrawal that achieved prompt criticality was completed in approximately 0.5 seconds, while the position indication system required several seconds to process and display the rod's new position. The monitoring system's response delay meant that the reactor achieved supercritical conditions before any indication of abnormal rod position became available to the crew. The reactor physics response to central rod withdrawal occurred on timescales that were fundamentally incompatible with human recognition or reaction capabilities. When the rod reached a withdrawal distance of approximately 20 inches above its normal fully inserted position, the reactor achieved prompt criticality with a neutron generation time of approximately 4 milliseconds. This condition resulted in exponential power increase that reached an estimated 20,000 megawatts in the first few milliseconds, following prompt criticality achievement. The neutron flux monitoring system experienced the same temporal mismatch that affected the position indication system, but with even more severe consequences for situational awareness. The neutron detectors positioned around the reactor core were designed to monitor gradual power changes during normal operations, with signal processing circuits that filtered rapid fluctuations to provide stable readings for control and monitoring purposes. These circuits were not designed to track the exponential power increases characteristic of prompt criticality conditions. When reactor power began its exponential increase, the neutron monitoring system's response was limited by both the processing delays inherent in the signal conditioning circuits and the saturation characteristics of the detection equipment itself. The neutron detectors reached their maximum output levels within the first few milliseconds of the power excursion, providing no useful information about the magnitude or progression of the excursion, beyond the fact that it exceeded the monitoring system's measurement range. The data recording systems that had faithfully documented the reactor's operational history experienced complete failure of their fundamental function during the most critical period of the reactor's existence. Chart recorders that tracked neutron flux, temperature, and pressure parameters were designed for gradual parameter changes occurring over minutes or hours. The exponential power increase and subsequent thermal effects occurred too rapidly for the recording mechanisms to track, creating a complete data gap during the period when recording was most needed. The crew's ability to recognize and respond to the developing emergency was further constrained by their physical position relative to the monitoring systems that might have provided early warning of abnormal conditions. The control rod lifting operation required crew members to be positioned on the reactor vessel head directly above the core, where they had no visual access to control room displays that might have indicated developing problems. The maintenance procedure had placed them in the worst possible location for recognizing the consequences of their actions. The reactor's audible alarm systems, which might have provided immediate notification of abnormal conditions, were defeated by the same temporal mismatches that affected the monitoring and recording systems. Alarm logic was based on parameter thresholds that assumed dangerous conditions would develop gradually enough for detection and operator response. The prompt criticality conditions developed faster than the alarm processing circuits could respond, providing no useful warning to the crew. The thermal effects that followed the initial neutron flux spike occurred with a time progression that briefly appeared to offer hope for recognition and control, but ultimately demonstrated the inadequacy of the monitoring systems for transient conditions. The reactor's power spike was terminated within approximately 4 milliseconds by the negative reactivity effects of fuel heating and steam formation. But the thermal energy deposited in the fuel during this brief period initiated a complex sequence of heat transfer and steam generation phenomena. Approximately 20% of the reactor fuel reached temperatures sufficient to cause melting, releasing molten material into the reactor coolant and initiating rapid steam generation that created pressure pulses throughout the reactor vessel. These thermal effects developed over time periods of tens to hundreds of milliseconds, approaching the response time limits of the monitoring systems but still occurring too rapidly for effective observation and recording. The steam formation that followed fuel melting created a water hammer effect that drove the reactor vessel's water inventory upward against the vessel head with sufficient force to generate peak pressures exceeding 10,000 pounds per square inch. This pressure pulse lifted the entire reactor vessel approximately 9 feet vertically, shearing all connected piping and instrumentation systems. The monitoring systems lost all connection to reactor parameters at this point, creating complete informational isolation between the reactor and its control systems. The expulsion of control rod shield plugs and reactor internals during the steam explosion created missile hazards that completed the destruction of the facility's monitoring capabilities. Chart recorders, control panels, and instrument displays were damaged or destroyed by flying debris, eliminating any possibility of post-event parameter reconstruction from recorded data. The monitoring systems that had failed to capture the initiating events were themselves destroyed by the consequences of those events. The crew members' positions on the reactor vessel head placed them directly in the path of the expelled reactor components and radiation fields that resulted from fuel melting and fission product release. 2 crew members were killed instantly by mechanical trauma from flying debris, while the third survived briefly but suffered fatal head injuries and massive radiation exposure. Their deaths occurred before any recognition of the developing emergency was possible. The complete failure of the monitoring and recording systems to provide useful information about the accident progression created unprecedented challenges for emergency response activities. First responders arriving at the facility found a reactor building contaminated with radioactive debris, but no functioning instrumentation to indicate reactor condition or radiation hazard levels. The emergency response had to proceed without any reliable information about what had occurred or what continuing hazards might exist. The accident investigation that followed would eventually reconstruct the sequence of events through forensic analysis of physical evidence rather than through recorded data. The central control rod was found withdrawn approximately 20 inches from its normal fully inserted position, with the control blade bound within its guide shroud at this position by deformation from the steam explosion. This physical evidence provided the only reliable information about the rod position that had initiated the accident. The investigation's reliance on forensic reconstruction rather than recorded data demonstrated the complete failure of the monitoring philosophy that had shaped the reactor's design and operation. The most critical reactor event in the facility's history had occurred in a temporal domain that simply did not exist within the monitoring system's design universe, creating a fundamental gap between the reactor's actual behavior and the information systems intended to observe and record that behavior. The reactor physics that governed the SL-1's destruction unfolded according to fundamental nuclear principles that had been well understood since the 1940s, yet the specific application of these principles to the reactor's unique design characteristics created consequences that exceeded all previous experience with nuclear excursions. The prompt criticality achieved through central control rod withdrawal initiated a cascade of physical processes that evolved through distinct phases, each operating on different timescales and each contributing to the system's rapid transition from controlled nuclear reaction to catastrophic destruction. The initial phase of the excursion was dominated by pure nuclear physics, operating on timescales measured in microseconds and milliseconds. When the central control rod reached a withdrawal distance of approximately 20 inches above its normal fully inserted position, the reactor's neutron multiplication factor exceeded unity by a margin sufficient to achieve prompt criticality. This condition meant that neutron production from fission reactions exceeded neutron absorption and leakage by a sufficient margin that the chain reaction could be sustained by prompt neutrons alone, without requiring the delayed neutrons that normally control reactor power changes. The reactor's neutron generation time, determined by the average time required for neutrons produced by one fission generation to cause the next generation of fissions, was approximately 4 milliseconds under the core conditions existing at the time of the accident. This generation time, combined with the excess reactivity introduced by rod withdrawal, resulted in a reactor period of approximately 4 milliseconds, meaning that neutron population and reactor power doubled every 4 milliseconds during the initial phase of the excursion. The exponential power increase that resulted from this short reactor period overwhelmed all normal reactor control mechanisms within the first few milliseconds of the excursion. The reactor's power level, which had been effectively zero during the shutdown maintenance condition, increased to an estimated 20,000 megawatts within approximately 10 milliseconds of achieving prompt criticality. This power level represented more than 6,000 times the reactor's normal full power rating, creating energy deposition rates in the fuel that exceeded the physical limits of the fuel materials. The energy release during this initial nuclear phase totaled approximately 133 megawatt-seconds, with most of this energy deposited directly in the reactor fuel through fission heating. The rapid energy deposition created fuel temperatures that reached or exceeded the melting point of the aluminum-uranium fuel plates in the highest flux regions of the core. Approximately 20% of the total fuel inventory experienced melting, with some fuel reaching temperatures sufficient to cause vaporization of both fuel and cladding materials. The termination of the nuclear excursion occurred through inherent physics feedback effects rather than through any engineered safety systems or operator actions. As fuel temperatures increased rapidly during the power spike, several negative reactivity mechanisms became effective. The thermal expansion of fuel materials decreased fuel density and reduced neutron moderation effectiveness. More significantly, the rapid heating of reactor coolant water created steam voids that displaced water moderator and reduced the neutron multiplication factor below unity, terminating the self-sustaining chain reaction. This self-termination occurred within approximately 4 milliseconds of the initial power spike, but the nuclear energy already deposited in the fuel initiated thermal and mechanical processes that would dominate the subsequent phases of the accident. The transition from nuclear excursion to thermal excursion marked the beginning of phenomena that operated on longer timescales but with consequences that proved equally destructive to the reactor system. The thermal phase of the accident was characterized by the transfer of energy from overheated fuel to the reactor coolant water, creating rapid steam generation that drove the mechanical destruction of the reactor vessel and surrounding systems. The molten fuel released into the reactor coolant provided a large surface area for heat transfer, creating essentially instantaneous steam formation that generated pressure waves throughout the reactor vessel. The steam generation rate during this phase far exceeded the capacity of any pressure relief systems to accommodate the expanding steam volume. The reactor vessel's pressure relief capabilities were designed for gradual pressure increases caused by loss of heat removal or other thermal transients, not for the rapid steam generation that resulted from molten fuel contact with water. The steam formation created local pressure spikes that propagated throughout the reactor coolant system faster than pressure relief valves could respond. The mechanical phase of the accident began when steam pressure buildup drove the reactor vessel's water inventory upward against the vessel head with sufficient velocity to create water hammer effects. The approximately 7 feet of water above the reactor core was accelerated upward by expanding steam, reaching an estimated velocity of 160 feet per second before impacting the vessel head. This impact created peak pressures exceeding 10,000 pounds per square inch at the vessel head, far exceeding the structural design limits of the reactor vessel and associated components. The water hammer impact transmitted sufficient momentum to the reactor vessel to overcome the weight of the vessel and its supporting structures, lifting the entire 40-ton reactor vessel approximately 9 feet vertically. This vertical displacement sheared all piping connections between the reactor vessel and external systems, including primary coolant piping, instrumentation lines, and electrical connections. The vessel's vertical movement also collapsed the guide tube structures that provided pathway for control rod drive mechanisms through the vessel head. The simultaneous pressure buildup within the reactor vessel expelled the control rod shield plugs that normally sealed the vessel head penetrations. These shield plugs, each weighing several hundred pounds, became high-velocity projectiles that struck the reactor building ceiling and caused extensive structural damage. The expulsion of shield plugs created large openings in the vessel head, through which reactor coolant, steam, fuel fragments, and fission products were expelled into the reactor building atmosphere. The central control rod assembly, which had initiated the accident through its withdrawal, was driven upward through the vessel head opening with sufficient velocity to impact the reactor building ceiling approximately 40 feet above the reactor vessel. The rod assembly penetrated the building's concrete and steel ceiling structure, with portions of the rod remaining embedded in the ceiling following the accident. This impact provided forensic evidence of the extreme forces generated during the mechanical phase of the accident. The reactor core structure itself experienced severe mechanical damage during the steam explosion and pressure wave propagation. The core support grid, which maintained precise positioning of fuel assemblies and control rod guide tubes, was displaced vertically by approximately 7 inches before being arrested by structural constraints. This displacement occurred during the initial pressure buildup phase and contributed to the binding of the central control rod at its 20-inch withdrawal position. The fuel assemblies within the core experienced varying degrees of damage depending on their location relative to the power distribution during the nuclear excursion. The central fuel assemblies, which experienced the highest neutron flux and energy deposition rates, suffered severe melting and structural destruction. Fuel assembly number 7, located northwest of the core center, experienced 73% fuel destruction, while other central assemblies showed destruction levels ranging from 50 to 80%. The non-uniform damage pattern throughout the core provided additional evidence of the power distribution effects that influenced the accident progression. Fuel assemblies located near the mispositioned cadmium shim strips experienced different damage levels than predicted by symmetrical core calculations, confirming that the reactor's actual neutron flux distribution differed significantly from design assumptions. This non-uniformity in damage indicated that local power peaking effects had influenced the energy deposition pattern during the excursion. The release of fission products from melted fuel created additional hazards that complicated emergency response and recovery operations. The steam explosion and pressure waves dispersed radioactive materials throughout the reactor building, creating contamination levels that required extensive protective measures for personnel entering the facility. The expulsion of reactor materials through the vessel head openings also released fission products to the reactor building atmosphere, requiring careful evaluation of potential off-site radiological consequences. The mechanical destruction of the reactor vessel and core structure created a configuration that was inherently subcritical and could not achieve criticality again. The expulsion of reactor coolant eliminated the water moderation necessary for sustaining a nuclear chain reaction, while the mechanical displacement and melting of fuel assemblies destroyed the geometric arrangement required for achieving critical configurations. This inherent subcriticality provided assurance that no further nuclear excursions could occur during subsequent recovery operations. The total energy release during all phases of the accident was dominated by the initial nuclear excursion, with the thermal and mechanical phases serving primarily to distribute and convert the nuclear energy into forms that caused physical destruction. The 133 megawatt-seconds of nuclear energy deposited during the first few milliseconds exceeded the energy release of conventional high explosives by factors of thousands, demonstrating the enormous energy density inherent in nuclear fission processes. The accident's progression through nuclear, thermal, and mechanical phases occurred with timescales that ranged from milliseconds to seconds, creating a complex sequence of coupled phenomena that challenged the traditional boundaries between nuclear engineering, thermal hydraulics, and structural mechanics. The rapid transition between these different physical domains demonstrated the inadequacy of safety analyses that considered these phenomena separately rather than as coupled processes. The forensic reconstruction of the accident required integration of nuclear physics calculations, thermal analysis of fuel melting, and structural analysis of the mechanical destruction to develop a comprehensive understanding of the failure progression. This multidisciplinary approach was necessary because the accident transcended the normal boundaries between different engineering specialties, creating failure modes that had not been previously observed or analyzed in detail. The physical evidence recovered from the destroyed reactor provided the only reliable information about the accident progression, since the monitoring and recording systems had failed to capture the critical phases of the event. The positions of displaced reactor components, the extent of fuel melting, and the damage patterns throughout the facility provided forensic data that enabled reconstruction of the accident timeline and energy release characteristics. The SL-1 accident demonstrated that reactor excursions could progress through multiple physical domains with consequences that exceeded all previous experience with nuclear system failures. The coupling between nuclear, thermal, and mechanical processes created destruction mechanisms that had not been anticipated in the reactor's safety analysis, revealing fundamental limitations in the analytical frameworks used to evaluate reactor safety. The emergency response that began within minutes of the SL-1 accident confronted unprecedented challenges that extended far beyond the immediate radiological and safety hazards. The complete failure of the reactor's monitoring and recording systems during the critical phases of the accident created a fundamental information void that compromised every aspect of recovery planning and stabilization efforts. Emergency responders and technical personnel were forced to develop entirely new approaches for assessing reactor condition and ensuring continued safety, without the comprehensive instrumentation data that had previously defined all reactor operations. The initial emergency response was triggered by automatic fire alarms that activated at 21:01 hours, but these alarms provided no indication of the actual nature or magnitude of the emergency. The alarm system's inability to distinguish between fire conditions and the steam explosion that had destroyed the reactor created immediate confusion about the appropriate response measures. Fire department personnel, responding to what they assumed was a conventional fire, encountered radiation hazards and facility damage that required immediate revision of their emergency procedures. The first responders entering the reactor building discovered extensive physical damage that provided visual evidence of the explosion's magnitude, but no functioning instrumentation to indicate current reactor condition or continuing hazards. Chart recorders that would normally provide immediate information about reactor power level, temperature, and radiation conditions were either destroyed or severed from their sensing elements. The emergency response had to proceed based on direct observation of physical conditions rather than the instrumented assessments that had governed all previous reactor operations. The establishment of radiation protection measures for emergency personnel required rapid deployment of portable monitoring equipment to replace the facility's damaged radiation monitoring systems. Health physics personnel used portable radiation detection instruments to map radiation dose rates throughout the reactor building, discovering levels exceeding 1,000 roentgens per hour in areas near the reactor vessel. These measurements provided the first quantitative information about the accident's radiological consequences, but they could not indicate whether these conditions were stable or continuing to evolve. The assessment of potential continuing nuclear reactivity represented one of the most critical uncertainties facing emergency responders. Without functioning neutron monitoring systems, technical personnel could not immediately determine whether the reactor remained subcritical or might achieve criticality again if water was added to the system. The visual observation of extensive fuel melting and core disruption suggested that the reactor geometry had been altered in ways that would prevent criticality, but this assessment required confirmation through alternative monitoring approaches. The deployment of temporary neutron detection equipment around the damaged reactor vessel provided the first reliable evidence that no significant nuclear activity was continuing. Portable neutron monitors positioned at various locations around the reactor building detected no neutron radiation above background levels, confirming that the nuclear chain reaction had been permanently terminated by the physical destruction of the reactor core. This information enabled emergency responders to focus on radiological protection and structural safety, without concern for additional nuclear excursions. The evaluation of potential steam explosion hazards required assessment of thermal conditions within the reactor vessel without functioning temperature monitoring systems. The visible damage to reactor vessel external surfaces and the severed piping connections indicated that significant thermal stresses had occurred, but emergency personnel needed to understand whether decay heat from fission products might create additional steam formation and pressure buildup. The absence of primary coolant system instrumentation prevented direct measurement of vessel temperature and pressure conditions. The installation of temporary temperature monitoring capabilities involved routing new thermocouple installations to accessible locations on reactor vessel, external surfaces, and remaining piping connections. These measurements provided limited information about average vessel temperature trends, but could not determine the internal temperature distribution or the thermal condition of remaining fuel assemblies. The temperature data indicated that vessel wall temperatures were decreasing over time, suggesting that no continuing heat sources were creating additional thermal hazards. The assessment of structural stability presented additional challenges that required engineering evaluation based on visual inspection rather than instrumented structural monitoring. The reactor vessel's 9-foot vertical displacement had created extensive damage to supporting structures and piping systems, but the vessel had returned to approximately its original position following the explosion. Emergency personnel needed to determine whether the vessel and building structures retained adequate integrity to support continuing recovery operations. Structural engineers conducting visual inspections of the reactor building and vessel support systems identified extensive damage to concrete structures, steel support members, and building systems, but concluded that the primary structural elements retained adequate integrity to support controlled access for recovery operations. The reactor vessel itself showed external deformation and impact damage, but appeared to retain structural coherence sufficient to contain remaining radioactive materials during recovery activities. The establishment of contamination control measures required extensive revision of normal radiological protection procedures to address the unprecedented levels of airborne and surface contamination created by the steam explosion. Standard contamination control protocols were designed for minor spills or equipment leaks, not for the dispersal of reactor core materials throughout an entire building. Emergency personnel developed new procedures for personnel protective equipment, decontamination processes, and contaminated material handling based on the actual conditions encountered. The recovery of the 3 crew members from the reactor building required specialized procedures that balanced the urgent need for emergency medical response with radiological protection requirements for rescue personnel. The crew members' high levels of radioactive contamination, caused by neutron activation and fission product contamination, created radiation exposure hazards for anyone attempting rescue operations. 2 crew members were found dead at the scene, while the third survived with severe injuries but died within hours of the accident. The radiological assessment of the crew members provided important forensic information about the neutron flux levels and duration of the nuclear excursion. Medical personnel using radiation detection equipment determined that the crew members had received massive neutron and gamma radiation doses that would have been fatal even without the mechanical injuries caused by the steam explosion. The pattern of neutron activation in the victims' bodies provided evidence about their positions relative to the reactor core during the excursion. The evaluation of potential off-site radiological consequences required rapid deployment of environmental monitoring capabilities to replace the facility's damaged meteorological and radiation monitoring systems. Mobile radiation monitoring teams conducted surveys of the surrounding area to detect any radioactive material that might have been released from the reactor building during the steam explosion. These surveys detected elevated radiation levels only in the immediate vicinity of the reactor building, confirming that significant off-site contamination had not occurred. The assessment of reactor fuel condition represented one of the most complex technical challenges during the initial recovery period. Without functioning neutron flux monitoring or core temperature instrumentation, technical personnel had to rely on indirect evidence to understand the extent of fuel damage and the potential for continued fission product release. The visible evidence of core damage and the radiological conditions within the reactor building indicated extensive fuel melting, but the full extent of core disruption could not be determined immediately. The development of specialized monitoring and sampling procedures enabled gradual characterization of the reactor's post-accident condition over the following days and weeks. Air sampling systems installed in the reactor building provided information about continuing fission product release rates, while radiation surveys of facility areas provided mapping of contamination patterns that reflected the steam explosion's material distribution effects. The planning for long-term reactor stabilization required development of entirely new procedures for managing a severely damaged reactor core without the benefit of normal cooling, monitoring, or control systems. Traditional reactor shutdown and decay heat removal procedures assumed functioning systems for water circulation, temperature monitoring, and contamination control. The SL-1's destroyed systems required innovative approaches for ensuring long-term stability of remaining radioactive materials. The implementation of alternative cooling methods involved routing temporary water supplies to provide heat removal from remaining fuel assemblies without risking additional steam formation or contamination spread. Engineering personnel designed systems for controlled water addition that would provide adequate heat removal while minimizing the potential for additional pressure buildup or radioactive material dispersal. The establishment of continuous monitoring capabilities required installation of replacement instrumentation systems that could operate reliably in the damaged facility's high radiation environment. Standard radiation monitoring equipment was not designed for the extreme conditions created by the accident, requiring modification or replacement with specialized instruments capable of accurate measurement in high radiation fields. The coordination of recovery operations among multiple organizations created additional complexities that had not been anticipated in pre-accident emergency planning. The accident response involved personnel from Combustion Engineering, the Atomic Energy Commission, Idaho Operations Office, military units, and various contractor organizations, each with different areas of expertise and operational procedures. The absence of comprehensive accident instrumentation data complicated communication and decision-making among these diverse response organizations. The development of accident investigation procedures required adaptation of standard investigation techniques to address the unique challenges created by the absence of recorded data during the critical accident phases. Traditional accident investigation relied heavily on analysis of recorded parameter trends and alarm sequences to reconstruct event timelines and identify causal factors. The SL-1 investigation required development of forensic techniques based on physical evidence analysis and theoretical reconstruction of accident physics. The preservation of physical evidence for detailed analysis required careful documentation and recovery of reactor components, facility structures, and contaminated materials that provided information about accident progression and effects. This evidence collection had to be conducted under severe radiological conditions while maintaining the integrity of materials that would be essential for understanding the accident's technical causes and consequences. The transition from emergency response to long-term recovery marked a fundamental shift in the technical challenges facing facility personnel. The initial response had focused on immediate safety and stability concerns, but long-term recovery required comprehensive understanding of reactor condition and development of procedures for permanent facility decontamination and decommissioning. This transition occurred without the benefit of normal reactor instrumentation to guide decision-making processes. The SL-1 accident recovery demonstrated the critical importance of alternative monitoring and assessment capabilities for managing nuclear emergencies that exceed the design basis of normal facility instrumentation. The successful stabilization of the damaged reactor was achieved through innovative application of emergency monitoring techniques, but the process revealed fundamental limitations in emergency preparedness planning that assumed continued availability of facility instrumentation systems during accident conditions. The forensic investigation of the SL-1 accident required development of entirely new methodologies for reconstructing nuclear reactor events without the benefit of recorded operational data during the critical accident phases. Traditional accident analysis techniques relied heavily on trending recorded parameters, alarm sequences, and operator logbook entries to establish chronological sequences and identify causal relationships. The SL-1 investigation confronted the unprecedented challenge of reconstructing a complex nuclear excursion using only physical evidence, theoretical calculations, and indirect inference from post-accident conditions. The initial forensic approach focused on detailed examination of the reactor core and vessel components to determine the physical processes that had occurred during the brief but destructive accident sequence. This examination required development of specialized techniques for accessing and analyzing highly radioactive materials under conditions that prevented direct human contact. Remote handling equipment and shielded examination facilities were established to enable detailed study of core components that retained lethal radiation levels months after the accident. The recovery of the central control rod assembly provided the most crucial physical evidence for understanding the accident's initiation mechanism. The rod was found withdrawn approximately 20 inches from its normal fully inserted position, with the control blade bound within its guide shroud by deformation that had occurred during the steam explosion. This physical evidence provided definitive confirmation that manual rod withdrawal had been the triggering event, but the investigation required additional analysis to understand why such withdrawal had occurred. The examination of control rod guide shrouds revealed extensive evidence of mechanical interference that supported the hypothesis that rod sticking had contributed to the excessive withdrawal. Shroud internal surfaces showed scoring marks and deformation patterns consistent with mechanical binding between control blades and shroud structures. These physical markings provided evidence that control rod movement had been impeded by mechanical interference, creating conditions that required application of additional manual force to overcome binding. The analysis of burnable poison strip condition throughout the core revealed extensive degradation that had not been adequately characterized during reactor operation. Physical examination of recovered poison strips showed buckling, cracking, and material loss that significantly exceeded the degradation levels that had been inferred from operational experience. The actual condition of these strips indicated that reactor shutdown margin had been more severely compromised than operational assessments had suggested. The detailed mapping of fuel damage patterns throughout the core provided information about the neutron flux distribution and energy deposition characteristics during the nuclear excursion. Fuel assemblies in different core locations showed varying degrees of melting and structural damage that reflected the power distribution effects during the brief period of supercritical operation. This damage mapping enabled reconstruction of the reactor's neutron flux profile during the excursion and provided validation for theoretical calculations of the accident physics. The forensic analysis revealed that fuel assembly number 1, which had been installed in core position 55, had accumulated only 253 megawatt days of burnup compared to other assemblies that had significantly higher burnup levels. This fresh fuel assembly created a local region of higher reactivity that contributed to power peaking effects during the excursion. The investigation determined that this fuel loading asymmetry had not been adequately considered in reactivity calculations and had contributed to the reactor's vulnerability to prompt criticality. The examination of reactor vessel structure and components provided detailed information about the mechanical forces and pressure effects that had occurred during the steam explosion phase of the accident. Vessel internal components showed damage patterns that enabled reconstruction of the sequence of mechanical events that had followed the initial nuclear excursion. The analysis of metal deformation and fracture patterns provided quantitative estimates of the pressures and forces that had been generated during the explosion. The recovery and analysis of expelled reactor components provided additional evidence about the energy release and mechanical effects during the accident. Shield plugs that had been expelled from the reactor vessel head were found embedded in the reactor building ceiling, providing forensic evidence of the projectile velocities that had been achieved during the explosion. The impact patterns and penetration depths enabled calculation of the kinetic energies involved in the component expulsion process. The radiological analysis of facility contamination patterns provided information about the distribution and characteristics of fission products that had been released during the accident. Air sampling and surface contamination surveys conducted over extended periods following the accident revealed the isotopic composition and quantity of radioactive materials that had been dispersed throughout the reactor building. This radiological forensics enabled assessment of the fraction of reactor core inventory that had been released and the effectiveness of facility containment during the accident. The medical examination of the 3 crew members provided crucial information about the neutron flux levels and radiation dose rates that had existed during the nuclear excursion. Autopsy results revealed evidence of neutron activation in the victims' bodies that enabled calculation of the neutron flux intensity and duration during the critical period. This biological dosimetry provided independent confirmation of the nuclear excursion characteristics that were inferred from physical damage analysis. The investigation of reactor operating history during the months preceding the accident revealed a pattern of degrading material conditions and increasing operational problems that had not been adequately recognized or addressed. Review of maintenance records and operational logs showed increasing frequency of control rod sticking events, particularly during the final month of operation, when the frequency increased from approximately 2% to 13% of rod movement attempts. The analysis of high-power testing conducted in the weeks before the accident revealed that reactor operation at power levels up to 4.7 megawatts had created thermal and radiation conditions that accelerated material degradation throughout the core. These tests had been conducted to evaluate condenser performance, but the investigation determined that the testing had significantly worsened core material conditions and increased the reactor's vulnerability to control rod binding and excessive reactivity insertion. The forensic examination of reactor design and safety analysis documentation revealed fundamental limitations in the analytical methods that had been used to evaluate reactor safety margins and accident consequences. The calculational models used for reactor physics analysis were acknowledged to be grossly oversimplified, due to the complex geometry created by irregular burnable poison distribution, leading to significant errors in predicted reactivity behavior and control rod worth estimates. The investigation determined that prompt criticality conditions had never been calculated for the reactor design, despite the known high reactivity worth of the central control rod. Safety analysis had focused on thermal hydraulic transients and loss of coolant accidents, but had not considered the possibility of rapid reactivity insertion through manual control rod manipulation. This analytical gap meant that the reactor's most dangerous potential accident condition had not been evaluated or protected against. The regulatory response to the SL-1 accident initiated fundamental changes in nuclear reactor safety analysis requirements and monitoring system design standards. The Atomic Energy Commission established new requirements for prompt criticality analysis, instrumentation system design, and emergency preparedness planning that address the specific deficiencies revealed by the accident investigation. These regulatory changes were applied not only to military reactors, but to the entire nuclear industry. The industry-wide impact of the SL-1 investigation extended far beyond the immediate regulatory changes to influence fundamental approaches to reactor monitoring system design and operational safety culture. The accident demonstrated that monitoring systems optimized for normal operations could create dangerous blind spots during abnormal conditions, leading to comprehensive revision of instrumentation philosophy throughout the nuclear industry. The development of enhanced reactor monitoring systems following SL-1 emphasized redundant instrumentation, faster response times, and comprehensive coverage of potential accident conditions rather than optimization for steady-state operations. New reactor designs incorporated multiple independent monitoring systems with overlapping measurement capabilities and response times adequate for detecting and recording rapid transients that had not been considered in earlier designs. The evolution of reactor safety analysis methodology incorporated lessons from the SL-1 investigation about the importance of considering coupled nuclear, thermal, and mechanical phenomena during accident progression. Safety analysis frameworks were expanded to include prompt criticality scenarios, steam explosion effects, and the potential for monitoring system failure during accident conditions. These analytical improvements required development of new computational tools and experimental programs to validate accident models. The influence of SL-1 on nuclear operator training programs emphasized the importance of understanding reactor physics and system limitations, rather than relying solely on procedural compliance and parameter monitoring. Training curricula were expanded to include instruction in reactor physics fundamentals, accident phenomenology, and emergency response under degraded instrumentation conditions. Simulator programs were developed to provide experience with accident scenarios that exceeded normal monitoring system capabilities. The long-term impact of the SL-1 accident on nuclear safety culture established principles that emphasized conservative decision-making, comprehensive safety analysis, and recognition of potential failure modes that had not been previously experienced. The accident demonstrated that complex technical systems could fail in ways that exceeded design assumptions and analytical models, creating a cultural emphasis on defense in-depth approaches and conservative safety margins. The forensic investigation techniques developed for SL-1 provided methodologies that were subsequently applied to other nuclear accidents and incidents where normal monitoring data was unavailable or inadequate. The approaches for reconstructing accident sequences through physical evidence analysis, theoretical modeling, and indirect inference became standard practices for nuclear accident investigation and influenced safety analysis methodologies throughout the industry. The SL-1 accident ultimately demonstrated that nuclear reactor safety required monitoring and safety systems designed for the worst possible conditions rather than for normal operations. The accident's most important lesson was that monitoring systems could create false confidence in safety margins while simultaneously creating blind spots for the most dangerous potential accident conditions. This fundamental insight drove decades of improvements in nuclear safety technology and operational practices that significantly enhanced the safety of nuclear power systems. The accident investigation revealed that the reactor's destruction had resulted not from a single cause, but from the convergence of multiple factors, including design limitations, material degradation, procedural inadequacies, and monitoring system blind spots. This system's perspective on accident causation influenced the development of probabilistic risk assessment methods and defense in-depth safety philosophies that became standard approaches for nuclear safety analysis. The legacy of the SL-1 accident extends beyond its specific technical lessons to encompass broader principles of complex system safety and the recognition that monitoring and control systems can themselves become sources of systemic vulnerability. The accident demonstrated that technical systems require safety approaches that account for the limitations of information systems and human cognition, not just the physical phenomena being controlled.